Hi there, welcome to my channel Mandu to Fundu. In this video, I'm going to discuss about the solution for counting the number of nodes in the complete binary tree. Let's look at the problem description. We are given a root of complete binary tree. We have to return the number of nodes in that tree. So the complete binary tree is the one which has almost all the levels except the last one are filled completely, and in the last level, if it is partially filled, it will be packed as far left as possible. So we have to design an algorithm that runs in less than order of n time complexity. So typically to count the number of nodes, we do the tree traversal, either the depth first traversal or breadth first traversal. Those two algorithms are order of n times. But in this case, they are expecting less than order of n time complexity. Let's see how we can solve this problem. First, we see the example 1. It has the 6 node tree, so the expected output is 6. If the tree is empty, then we have to return 0. If the tree has only one element, then we have to return 1. So the number of nodes in the tree is ranging from 0 to 50,000. The value of the node is also ranging from 0 to 50,000. The tree is guaranteed to be complete. So we are given this input tree which has 9 elements. So the expected output is 9. In order to count the number of elements in the tree, we have to do the traversal. So we have to pick up either depth first traversal algorithms or the breadth first traversal and then modify it such a way that we get less than order of n time complexity. We can use the level order traversal algorithm and add some extension code to that to make it less than order of n time complexity. So first we initialize the count, and instead of incrementing the count when we process the node, what we have to do is increment the count whenever the node is added to the queue, which will be processed later during the traversal. Okay, so that is one part. The second part is whenever we process a node in a particular level, we have to check whether the next level node has any children, meaning the current level's grandchildren are present or not. We have to check that. If there are no grandchildren present for a particular level, that means the immediately following level is the last one that needs to be traversed. Skip the traversal for the last level. Thereby we can always achieve less than order of n time complexity. For example, in this case, when we process the level 0, we have grandchildren for level 0, which is in level 2. And then when we process the level 1, we have the grandchildren at level 3. When we process the level 2, there are no grandchildren. So we can skip traversing these two. The reason is we already account the nodes in the count variable when we add the node to the queue. Let's look at the flowchart. Input for this procedure is the root of a binary tree. First we initialize the count to 0, and then we check whether the root node is null. In that case, we simply return the 0 as the number of nodes in there. Otherwise, we initialize the queue and add the root node to that queue and initialize the count to 1. As I said in the problem description section, whenever we add an element to the queue, we increment the count. So we are incrementing the count here. Next, we check whether the queue is empty. This is the beginning of the outer loop. So this outer loop prepares the data for traversing the current level, like the number of elements to be processed for that level. Whenever we enter the outer loop, we initialize the queue length to the current number of elements in the queue, and then we initialize the grandchild exist boolean to false. Then we enter the inner loop. Here we check whether the queue length is greater than 0. In that case, we go ahead and dequeue the first element in the queue, and we check whether that dequeued element has the left child. The current dequeued element has the left child, then we add that left child to the queue and increment the count variable. So whenever we are adding it to the queue, we are incrementing the counter. And then we check whether there is a grandchildren through this left child that was added just now. If so, we set the grandchild exists flag to true. Otherwise, we go ahead and try to add the right child if it exists. If it exists, we add the right child and increment the count. Then we check whether there is any grandchildren through that right child. If so, we set the grandchild exists to true. Then we repeat this until all the elements, the queue lane number of elements are processed. Once the queue lane is 0, then we come out of the inner loop and we check whether the grandchildren exist flag is false. That means the next level elements are all leaf node. So we can break out of the outer loop and return the count. Otherwise, we keep processing the elements in the next level. Once all the elements are processed, then we come out and return the count value. Let's move on to coding. First I initialize the count to 0. Then I check whether the root is null. If so, return the count. Otherwise, initialize the queue and add the root node to that queue. Then set the count value to 1. Then I enter the for loop. This will run until the queue has some element in it. So in each iteration, I assign the total current number of elements in the queue in queue len variable, and then initialize the grandchildren exist flag to false. This is to check whether the current level nodes have a grandchildren at the end of this iteration. Next we enter the for loop, inner for loop, which runs queue len number of times to process the queue len elements in the queue. So first I dequeue the first element and assign that to cur, and then update the queue size. Then I check whether the current element has a left child. If so, increment the count and then add the left child to the queue. And then I check whether this current left child has a children, that is the grandchildren of the current node dequeued. We check whether the current left has the left child or right child. In either case, we update the grandchildren exist flag to true if there is a children. Next I check whether the right child exists for the current node. If so, increment the count and then add that right child to the queue, and then again check whether there is a grandchildren for the current node through this right child. If there is a children, then I mark that grandchildren exist to true. Then I decrement the queue len count. Once we come out of the loop, I check whether the grandchildren exist is false. In that case, all the next level elements are the last level nodes in the tree. So break out of the loop, we do not have to process those nodes. Once we come out of the outer loop, I return the count. Next I'm going to run the test cases. all the tests passed. Next I'm going to submit this program. Cool, this program is accepted. Next I'm going to do the code walkthrough with sample input. We are given this input tree which has 9 nodes, so the expected output is 9. So first we initialize the count to 0 and we check whether the root is null. In this case it is not, it is null. We go ahead and initialize the queue with the root node as the first element in it, and we update the count to reflect that. So whenever we add a node to the queue, we have to increment the count. Count is 1 and the queue has node 10 in it. So the red indicates the elements which are present in the queue. Then we are entering the outer loop. Here we are checking whether the queue length is greater than 0. Yes, it is. It has one element. So we are entering the loop and we are initializing the queue length so that many number of elements will be processed by the inner loop, that level. Okay, queue length will be 1. We initialize the grandchildren exist boolean to detect the condition where the current level has do not have any grandchildren or not. So this variable is for checking whether the current level nodes have a grandchildren or not at the end of this inner loop, at the end of the current level processing. Okay, so initially we set that boolean to false. Then we are entering the inner loop. So the inner loop iterate over all the elements in the queue. Each iteration it dequeue the node from that queue and then update the queue. Then it checks whether that node has a left child or not. If it has a left child, it has 20. So then that node will be added to the queue and then the count will be incremented. Whenever we added the node, we increment the count. Then we add the left child to the queue and then we check whether there is a grandchild for this current node through this left child. So the current left of left is non-null and current left of right is non-null. If either one of them is true, that means the current node has a grandchild. So we mark that as true. Same thing we do for the right child. So if the right child exists, we increment the count and add it to the queue. We have 30 in it. So right now 20 and 30 are in the queue. So this diagram in the loop iteration depicts at the end of each iteration what is the state of the tree and the queue data structure. So right now we are processing level 0. So once we add that right child to the queue, then we check whether any children that right child has. That means the current node has a grandchildren through right child as well. So the 30 has a grandchildren. The 30 has a children. So we mark in that case also the boolean to true. Then we decrement the queue length count so that we process as many number of elements at the time of entering this loop. Once all the elements in that current level, that is in this case only one node was present in the queue when we enter the 0th iteration in the outer loop. So after the 10 is processed, we come out of the loop and we check whether all the nodes processed in that level has a grandchildren or not. So right now this is for true because the node 10 has children. So we move on to the next iteration and where we process these two elements. So when we leave the iteration 0 in the outer loop, we have 20 and 30 in the queue and the count is 3. So far we visited root and the left child and the right child. So 3. And then the grandchildren exist is true because these two nodes have children. Okay. Next we will be processing the node in level 1. So in the case of level 1, when we do the same thing. We initialize the queue length. In this case it is 2, and then the grandchildren exist will be reset to false. So it will be reset to false, and then we enter the inner loop. Here we check, we first dequeue the 20, and then we check whether the 20 has a left child. Yes, it is having 40, and then it is having 50. So both those two nodes will be added to the queue, and then the queue length will be decremented, and then the count will be incremented once for this 50 and once for this once for this 40, once for this 50. So right now the count is 5, and because this 40 has children, we mark the grandchildren exist as true because of this condition. Next we add the right child into the queue, and then we check whether it has a left or right child. It does not have any children, so we will not updating anything here. We just move on to the next iteration. Okay. Then in the next iteration of the inner loop, we dequeue the 30, and so the dequeued the 30, the current element is 30, and then we check whether it has a left child. If in that case 60 will be added to the queue, and it also check whether it has a right child. The 70 also added to the queue, and then for each of the children the count will be incremented once. So the count becomes 5 to 7 to account these two children, because when we process the 40, whatever the grandchild exists flag we set, that will be there until we process all the elements. So when we come out of this inner loop, what we have is all these elements in the level 2 will be in the queue, and the count is 7. We have visited so far 7 nodes, and then the grandchildren exist flag is marked as true because the 40 has 80 and 90. This condition is not met, so we continue with processing the node in the level 2. Okay. So in the outer loop iteration 2, we process the node in the level 2. Okay. So when we enter, the queue length is set to 4, and the count is 7, and the grandchildren exist flag is reset to false. Okay. So here first node when we enter the inner loop, we dequeue the first element, which is 40. We check whether it has a left child. Yes, 80 will be added to the queue, and I think here it will be 90 also, because when we process this node, we add both the nodes when we come out of this iteration 0. So we add 80 and 90 into the queue, and then the queue length will be decremented, and the count will be incremented to 9 to reflect these two nodes. Same thing here. After adding these two nodes into the queue, we check whether they have the children in here, but both the nodes do not have any children, so the grandchildren exist flag will be still false when we exit the inner loop iteration 0. Okay. So count will be 9, and the current node we pick up in the iteration 1 is 50, and we check whether 50 has left child. It doesn't have right child either, so we decrement the queue length, and the queue length become 2. Next we dequeue number 70. We check whether the 70 has a left child. 60 it doesn't have any left or right child, so we decrement the queue length, and without updating any the grandchild exist flag. The last element 70 in that level is picked, and the count will be we check whether it has a left or right child. It doesn't, so we simply decrement the queue count. That becomes 0, and the count is still 9, because now we already so far we added 9 elements into the queue, but we haven't visited these two nodes yet. Like in the inner loop, in the outer loop, we skip the last level. So when we come out of this loop, the grandchildren exist in this outer loop iteration is false. At the end of processing the level 2, we have 80 and 90 in the queue, that is in the level 3, and the count is 9. We have already added 9 elements in the queue so far, so that's what it reflects. That is equal to the total number of elements in the tree. And then the grandchildren exist flag is false, because these two nodes do not have any children. So when we check that condition, we break out of the loop. So thereby we are not processing this level at all. We always skip the last level because of this check. Okay, so thereby when there is a 9 elements in the tree, but we do only process only 7 nodes, and we are able to compute the total number of nodes in the tree. So the time complexity of this algorithm is it's less than order of n. Next I'm going to do the time and space complexity analysis for this solution. Let's do the time complexity analysis for this input. So in this traversal algorithm, the main processing is done by the code inside the inner loop. For example, it dequeues the node from the queue, and then it checks whether that the current node has a left child. If so, it increments the count, and then it adds the left child, and then it checks whether it has a grandchildren or not. All these processings are done only inside the inner loop. Okay, so let's see how many times this loop has to run. As per the code flow part, we have seen that 7 nodes added their childrens into the queue. For example, the root node adds these two, this node adds these two, this node adds these two, and this node adds these two, and these 3 nodes do not have any children, but still they check, they come inside, they check whether they have a left child or right child, and all these checks. Okay, so totally 7 times this inner loop executes in order to compute the total number of elements in this tree. Okay, for 9 elements, the number of times it has to run is 7. So this is actually the number of intermediate nodes in the tree. If we generalize that, except the leaf node, all other nodes are attempting to add their children into the queue. So the number of intermediate nodes in the tree is 2 to the power height of the tree minus 1. So in this case, the height of the tree is log n, log 9, so which is 3, 2 to the power 3 minus 1, 7. So the time complexity for this algorithm is order of 2 to the power log n minus 1. This is less than order of n. Okay. Now let's look at the space complexity for this procedure. Assuming if this level also is complete, how many nodes will be here? 2 to the power 3, 8 nodes will be here, correct? When we process the nodes in this level, at most 8 nodes will be in the queue, which is equal to the number of leaf nodes in the tree. So the number of leaf nodes is order of 2 to the power log n. So the space complexity for this algorithm is order of 2 to the power log n. Thanks for watching this video. Have a great day.